Hello everyone, my name is Marko Pavlic from the Machine Vision and Perception Group of the Technical University of Munich, and I'm going to introduce my paper, RobotScale, a framework for adaptable estimation of static and dynamic properties with object-dependent sensitivity tuning. For our approach of learning from human demonstration, we use passive visual perception to track human motion and object poses and use this to segment tasks and to learn skills to be able to execute them on the robot. What we miss with the passive visual perception is information about the physics in the environment. That's why we use the robot and its tactile sensors to estimate the missing physics. And RobotScale is the first module to estimate static and dynamic object properties. First of all, we need to estimate the wrench in the end effector, which we can do using a torque-controlled robot, since adding a payload changes the parameters of the end effector, which leads to a torque change compared to the unloaded case. And using the robot Jacobian, we can estimate the wrench in the end effector. In addition, we equipped the fingertips of the robot with force torque sensors, and we can transform the measured forces Fi into the end effector frame. And by summing all the measurements, we can also estimate the wrench in the end effector. The next step is to model the rigid object dynamics using Newton-Euler. Having now the measurements of the robot and the dedicated force torque sensors, we can rewrite the rigid object dynamics into regression form, as you can see here, with PL, a vector for all the unknown object parameters. And using least squares estimation, we can calculate the unknown object parameters. Here you can see now our hardware setup. So we have RGBD cameras for the human and object tracking. We have a torque-controlled robot with providing joint torque measurements, and we have the force torque sensors in the fingertips. Our experiments focused on light objects from 90 to 480 grams, since for heavier objects, the literature already showed good result using joint torque measurements. In the video in the middle, you see the static measurements done by the robot, where the correct center of mass is marked with a red cross. After the robot did the static experiments, on the left, the unknown parameters will be updated, and the robot will also show the correct result by regrasping in the correct center of mass. On the right, you see the robot performing the shaking motion to estimate also the dynamic parameters. The results we achieved for the static parameters showed that the fingertip force torque sensors outperformed the robot as a sensor, and also that the robot as a sensor achieved better results for heavier objects. For the dynamic parameters, no correct estimation using the robot joint torque measurements was possible, and also the error for using the fingertip force torque sensors was quite high, with 15% error to the ground truth. First investigation showed that the acceleration estimation, which we are doing using the joint velocity measurements, influences both approaches and needs to be solved in next steps. We also looked at the sensitivity of the robot as a sensor, and we saw that good joint configurations with better results are proportional to small condition numbers of the robot Jacobian. So adding tactile information is a crucial part for learning from human demonstration to be added to the passive visual perception. And we showed that we can estimate object parameters for a wide variety of unknown objects using the robot and force torque sensors, and the framework is extendable for different hardware. But improvements for the acceleration measurements need to be done to get better results for the dynamic properties. In future work, we will try to estimate also mass distribution. We'll work on estimation of rigidity of objects, and we want also to handle fluids. Thank you very much for your attention, and I'm happy to answer your questions during the conference or via email. Thank you.